All right, let's look at a more involved example this time. Um, so here we have a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So what we're going to interpret that to mean in this case is basically minimize the surface area of the can, right? So in that case, we want to draw a can here, a cylindrical can. So something like this. Right. And let's say, well, what is our objective? Our objective is the surface area. So, objective. For surface area here, let's just use S. You can call it SA or A, or, it's entirely up to you what you want to use at any point. Right, but I'll use S. Now, when we're finding the surface area of this thing, remember that there's really 3 pieces to this. We have sort of the top, the side, bottom. Right? Some optimization problems will specify, a box with no top or a can with no top or something like that. But in this case, nothing of that sort is specified, so we're going to assume it has all 3 pieces. Okay. So how do we find the area of all 3 of these? Right. Well, the top and bottom are pretty easy. They're just areas of a circle, right? What we do need to do is specify some quantities here. So we'll say that this cylindrical can has radius r and height h. Okay. Now once we've done that, then the area of the top and the bottom of the can is pi r squared, because they're just disks, they're just circles. And we have 2 of them, so we get 2 pi r squared. Okay, so that's the area of the top plus the area of the bottom. Okay, now to get the lateral area of this cylinder, what we actually do is we basically just say, well, okay, we're going to take the length of the bottom and multiply it by the height. Right? It's the same kind of principle to find the area of any sort of thing. In some sense, you just take the length times height. Right? So, because you can also imagine cutting this cylindrical can along the side and flattening it to a square, and then you can really see that, it's length times height. Right? And so in this case, when we're doing length, the height is obviously h. The length, well, the length is the length of a circle of radius r, which is the circumference. So we have 2 pi r. Right? That would give us the length around this circle here, and then times the height. Okay, so that's our objective function. Okay. Now we need our constraint. Right? So the constraint here, so for the constraint here, we need to sort of get our units straight. Okay, so one thing I want to specify here is that 1 liter is equal to, say, 1,000 cubic centimeters. Okay. And in that case, then we're going to measure the radius and the height in terms of centimeters, right? So if 1 liter, right, if 1 liter is 1,000 cubic centimeters, then our constraint, this should be the volume of this, right? So the volume of this can has to be 1 liter or 1,000 cubic centimeters. So the volume of a cylinder is just, we take the area of the base and we multiply by the height. So we get a pretty simple expression here. Pi r squared times h equals 1,000. Right? And then now the procedure is going to be sort of the same as before. right? We need to solve the constraint here for some variable. We can use either one, really. It's usually a good idea to pick the one that's sort of easier to do. So here, h is easy to solve for. So let's solve for h. This is 1,000 over pi r squared. Okay. So now that we have that, we're going to take it and we're going to plug it into the objective function, just like we did before. Okay. So the objective, this now becomes s equals 2 pi r squared plus 2 pi r times 1,000 over pi r squared. Right, and then let's see, what can we cancel here? The pi's cancel, this r cancels the square. And so we can simplify this to be 2 pi r squared plus, oh, I guess we have 2,000 for r. Right. Now, what we did in the last case was we said, okay, well, what kind of interval made sense, right? What's the lowest and the highest r can be? Really, the only restriction we have here is that r has to be bigger than 0, right? Often a good way to check is say, all right, let's take, the objective function here and set that equal to 0. Those are usually the good places to say, like, all right, here's where we should start our variable. Here's where we should end it. As long as we, this function will never equal 0, is my point here, because of this 2,000 over r. It can be negative, and it is positive. It's not defined at r equals 0. So basically we just have to pick, do we want r less than 0 or r bigger than 0? So here, we're going to say the feasible domain here is just r is greater than 0. Right? That's all we can say. Right? So now we don't have any endpoints. We can't do any tricks like that. So we have to reason out a way to find the solution. Right? But, we might be okay still. So let's look for critical values and our critical numbers and see, what happens here. When we try and find critical numbers, what's going to happen? Okay. So let's do it. Right, so s prime. So we're taking the derivative of this thing over here. So s prime is going to be 4 pi r minus 2,000 over r squared. Right, if we take the derivative of this function up here. Okay, so we still want to do the same thing as usual and set this equal to 0. Now, we often check here, right? Where is this derivative undefined? But since we're looking on the domain here, r greater than 0, this function would be undefined if r were 0, but that's not in the domain anyway. So we don't have to worry about that. So we just want to set this equal to 0. What will make our life a little easier here is to combine this into one fraction. Right? So if we combine this into one fraction, we have to multiply this part by r squared over r squared here. And that's going to give us 4r cubed, or 4 pi r cubed, and then minus 2,000 over r squared. Right, so give them a common denominator. And now we can set this equal to 0. And, for a fraction to equal 0, we just set the top equal to 0. 4 pi r cubed, minus 2,000 equals 0, which basically now is going to boil down to r cubed equals 2000 over 4 pi. Or again, we can simplify it more, 500 over pi. Right? So in this case, we take a cube root. There's only one of them. And so this is our critical number. So the important thing here is that we have exactly one critical number. Okay. So why is that important? Well, if we had multiple critical numbers, our function can do all sorts of weird things, right? We could have a local minimum somewhere, but then a local maximum somewhere else. And, it'd be impossible to definitively say that, the function doesn't get smaller than that local minimum we found, right? It might sort of go, it could do something like, say, go down, we have a local minimum, then go up, and then go down a lot like this. And there's no way to tell that if we have more than one critical number. But let's look at this here, right? What we want to do is say, like, well, what's going on with the function s, right? Where is it increasing? Where is it decreasing? Okay. So we know that s prime is equal to 0 at this value here, right? If we say plug in s prime, let's say compute s prime of 1. Okay. If we plug that in, we're going to get a negative number, right? If we plug 1 into s prime up here, into this thing, we're going to get a negative number. All right. On the other hand, let's see, 500 over pi, what about is our cube root of 500 over? So let's see, what's a good number that's bigger than that? Say 500 over pi is probably close to, so let's say 200. I don't know. Maybe even 100 would be fine. But if you take 200 and you plug that into this function, you're going to find out that this is greater than 0. Again, these values are probably too far away, but it doesn't really matter because the derivative is only equal to 0, 1. Right, so we're basically doing the first derivative test here, right? What we do here is we're saying, well, okay, we don't want that arrow. We say, all right, here's r equals 0. We don't care about that one. Here's cube root of 500 over pi. Okay. We know that s prime is 0 here. It's positive over here and negative over here. Since we know that, we can sort of definitively now say that, well, we don't have endpoints here, but we know that the function is always going down over here and always going up over here. So we have to wind up with something vaguely like this. Right, it's probably not exactly a parabola. You can graph it in Mathematica and see what's going on. But we know that it has to go down until this point, and then it has to go up. So we can definitely 100% for sure say that r equals cube root of 500 over pi. This is an absolute minimum on 0 to infinity, right? Because it's the only critical number, and we've sort of verified by the first derivative test that it is, in fact, an absolute minimum. And, you know, those two things together say, well, this is the only option. So, let's see. So let's write down our radius. Then our 1,000 over pi r squared. H 1,000 over pi cube root 500 over pi squared. Let's see here. So that's some number. So we'll say here that the can has a radius of cube root 500 over pi and height 1,000 over pi cube root 500 pi squared. These are both in centimeters here. Okay. In this case, it wouldn't be necessarily a bad idea to get some decimal approximations here. So let me do that real quick. Let's see. So 500 over pi 1/3. Let's see, what is that numerically? So this is about 5.419 centimeters. And then the other one, 1,000 over pi times this quantity squared. So the height is about 10.839. Right. So, you know, in this case, we're kind of like making real world measurements here. So it's typically a better idea to do some approximation of that. All right. So that will conclude this example.